Assalamualaikum. My name is Muhammad Ali Husaini bin Abdul Rahman, matrix number E22A0431. I will start the presentation with introductions. For introductions, UV visible spectroscopy is a crucial tool for detecting contaminant in the aqueous environment. Based on the Lambert-Spear law, an adaptive wireless sensor network, which is WSN, is used for water quality monitoring and drinking water source. The WSN consists of stationary and mobile nodes equipped with UV visible spectrometer probes. The probes measure UV visible absorption spectra, quantifying water quality parameters like TOC, nitrates, and turbidity. The dual PSO algorithm triggers pollution source localization if a pollution event is detected based on the spatial temporal distribution of water quality parameters. The algorithm computes multi-parameter concentration and uses particle swarm optimization to locate pollution source. That's all from me. Thank you.
Okay, for my part is a sample process. The sampling process for water quality monitoring in drinking water source areas use an adaptive wireless sensor network WSN with UV visible spectrometer probes. These networks include stationary BIOS, BUOYS, and mobile unmanned surface vehicle. All equipment with spectrometer probes that can adjust their optical path length for reliable measurements across various pollutant concentration. During routine operation, each node measures UV visible absorption spectra of water and process this data locally to quantify multiple water quality parameters. If a pollution event is detected, a dual PSO algorithm is triggered. This algorithm has two functions. First, it computes multi-parameter concentration through spectral decomposition on each node, and it uses the mobile nodes to search for pollution source based on concentration distributions. The system identifies the most sensitive indicator of pollution by calculating parameter entropy, and then guide the mobile nodes to localize the source position corresponding to the maximum concentration of this indicator.
As for the sample preparation in case of water quality monitoring, it is likely to include the following step here. The first step is collection, where the actual water samples are drawn from the specific region of study. This could be from different dates, site, or time to map space, and time separately for water quality. Second is preservation. It is needed in occasion where the sample must be preserved to avoid any change in the content of analyte before the analysis begins. This could be through incorporating additives such as preservative or some other methods like storing the sample under some certain condition. For example, storing them under cool temperatures. Filtration is the next step, which aims to eliminate particles that may cause some interference to the spectroscopy analysis by filtering sample through membranes of a specific pore size. This step helps to eliminate all the prejudicial characteristics of water sample and get totally dissolved right ready for analysis. For its dilution, due to the fact that the concentration of the analytes may be beyond the capabilities of the given instrument detection bed, and therefore it has to be diluted using high purity water or inappropriate solvent. The fifth one is pH correction, because some tests call for a sample to have a specific pH to serve as a baseline measure. This may require incorporation of acid or alkali to bring the pH of the sample to an acceptable value. Next is digestion. In some cases, for instance the determination of total organic carbon, the sample matrix may have to be decomposed to convert the organic materials into forms suitable for the measurement by the UV. Finally, there is the step 7. The prepared sample is then introduced into the UV visible spectrometer for analysis. The follow-up optical plate has an adaptive ability for altering in response to the concentration of the analyte.
Wavelength lambda can be expressed as A lambda I equal log 10 lambda I per IT lambda I equal K lambda I B IT. The length of the optical plates, the concentration of the absorbing component, and the absorption coefficient or effect absorption. Logarithmic. The results show absorption A lambda I for absorbing component I and wavelength lambda can be expressed as A lambda I per log 10 I per IT lambda I equal K lambda I BCI. The length of the optical phase, the contraction of the absorbing component, and the absorption coefficient all affect absorption. So, for a logarithmic formula that sums the contribution from each component is used to determine the total absorption at a given wavelength. The wavelength range of 200 until 800 nanometer is where the spectrometer works. The spectrometer reduces the error from the Beer-Lambert equation by measuring absorption correctly over a range of contraction by changing the optical phase. Measurement can be made with accuracy and reliability because these corrections are made in situ. Okay, so next, as seen in figure 4, the solution scenario is construct. 9 stationary nodes are consistently placed in fixed place along the 3,000 meter long and 3,000 meter wide sensing pair. Why? 9 mobile nodes are randomly placed and move with the wave. Let the sync node collect location coordinate and multi-parameter readings from all wireless sensor nodes while identifying the sources of water pollution, then sense the plane rotate to the mobile node curve, the observed absorption curve, and the contribution of multiple parameters, demonstrating a high degree of accuracy in estimating the absorption curve. So the additional multi-parameter sample were taxed to assess the effectiveness of the adaptive optical pace. So next, for a specific multi-parameter sample containing 60 mg per liter TOC, 8 mg per liter nitrate nitrogen, 2 mg per liter nitrate nitrogen, and 20 NTU turbidity is test. The result confirmed the high accuracy of the quantification process, highlighting the system ability to simultaneously measure and analyze multiple parameters effectively. So this demonstrates the potential of the UV visible spectrometer in providing precise and reliable data for various applications. The result demonstrates our method enhanced quantification performance, particularly when optimizing the optical phase. The design UV visible spectrometer probe combined with the dual PSO algorithm ensure optical fitting across the entire spectral range, reducing deviation from the Beer-Lambert law. Consequently, RE and RSD are lower and more stable across a wide range of pollutant concentration. So, moreover, our method enables simultaneous and rapid quantification of multiple parameters without requiring extensive computational resources.
Assalamualaikum and hi, my name is Kilisha. So now I'm going to continue to present about the result analysis. Okay, this case study provides a comparison of multi-parameter quantification using two analysis methods, namely dual PSO, particle swarm optimization, and LSSVM, least square support vector machine. The data displayed in table 1 includes three main parameters, namely TOC, total organic carbon, NO3/N, nitrogen nitrate, and turbidity at the various concentrations and different optical paths. There are two important metrics used to evaluate the performance of these two methods are relative error, RE, and relative standard deviation, which is RSD. Okay, so now let's move to the next. Okay, figure 9 shows the distribution of various simulated water quality parameters, including TOC, NO3/N, and turbidity. TOC is identified as the most sensitive parameter to water pollution because it is easily affected by the presence of organic matter. Dual PSO algorithm is used for quantitative analysis of these parameters, which works on wireless sensor nodes and sync nodes to find and determine the location of pollution sources. In the analysis of the entropy distributions of various parameters, it was found that the entropy of the TOC was always lower than the NO3/N and turbidity. This shows that the lower disturbance of TOC has made it an effective metric to identify the parameters that are most sensitive to pollution. Okay, so now I'm going to talk about the figure 10. Figure 10 displays the entropy distribution of various water quality parameters during the search. The figure shows that the entropy of TOC distribution remains lower than that of the nitrogen nitrate and turbidity. The difference becomes more noticeable with a more detailed distribution during the search. This shows that entropy is an effective metric to recognize the most sensitive parameter, which in this case is TOC. A lower entropy indicates a lower degree of interference, indicating that TOC is more indicative of water pollution sources than other parameters. Next is about a figure 11. Figure 11 is about compares the dual PSO algorithm with the GA, which is genetic algorithm, in finding water pollution sources. The analysis shows that dual PSO features a faster and more stable convergence curve and reaches the optimal state with a lower number of iterations than GA. In terms of the path length of moving nodes, dual PSO produce a shorter and more consistent path. This reflects a higher coefficient in routing of sensor nodes. On the other hand, GA requires a longer path for which it shows a lower efficiency. Overall, dual PSO is a better choice than GA for detecting water pollution sources due to its higher convergence speed and routing efficiency.
This study utilized a UV visible spectrometer probe and adapter optical path for water quality monitoring in a wireless sensor network. The probe offers fast response, in situ multi-parameter analysis, no secondary contaminant, and low maintenance costs. The adapted optical path mechanism adjusts dynamically based on pollutant concentration, optimizing sensing performance and maintaining accuracy across varying conditions. The real-time adjustment of the optical path ensures accuracy measurement regardless of contaminant levels, with enhanced reliability in dynamic environment. This approach aims to provide accuracy real-time monitoring of water quality, especially during pollution accident, ensuring more reliable and meaningful results in surface water analysis.
Assalamualaikum. My name is Muhammad Aiman Fitri bin Muhammad Noor. Metric number E22A0444. Okay, I would like to continue the description of analysis technique using UV visible instrument part. The absorption curve from spectrometer probes are analyzed using UV visible spectrum decomposition in wireless sensor networks for water quality monitoring. Using this method, the curves are divided into two primary parts: the characteristic curves, which are the distinct spectra of substance like nitrate, nitrogen, or TOC, and the background curve, which shows baseline absorption. The method makes concentration measurement easier by determining each substance contribution to the overall growth by computing proportion coefficient. This method for mixture analysis greatly improve the accuracy of water quality assessment by allowing the simultaneous identification and quantification of several chemicals in complete water samples.
For conclusion, this paper proposed a method using wireless sensor networks to efficiently identify and locate water pollution sources. The dual particle swarm optimization algorithm handles multi-parameter measurement, recognizes pollution, locates pollution sources, and adjusts optical paths. The system used distributed processing, entropy metrics, and optical path adjustment. Experiment show this method improve multi-parameter analysis accuracy, speed up pollution source discovery, and is scalable. Future research will expand this method to handle multiple sources and mobile pollution. That's all from us. Thank you.